Okay, final problem for 311. Remember 311, we're talking about related rates. We're looking at rates of varying functions, and often we're given a rate and we're asked to find a rate. And this is problem number 4, the sliding ladder problem. This is one of the more common problems that AP likes to ask when it comes to related rates. So again, you're just going to make sure that you pay close attention, that whatever I'm drawing, you're drawing. Remember, you can use these notes when we go to take our quiz. And as always, make sure that you're asking me questions in class if you're unsure of why I'm doing what I'm doing. Okay? All right. It says a 5-meter ladder leans against a wall. The bottom of the ladder is 1.5 meters away from the wall at time t equals 0. This is the first problem where we are given time values. In every other problem, we are just told at a particular moment, and we were never told that specific moment in time. And notice in this problem we are, so that feels interesting already. Okay, so the bottom of the ladder is 1.5 meters away from the wall at time 0, the initial distance, and slides away from the wall at a rate of 0.8 meters per second. Again, I know the 0.8 is a rate because it tells me that, and I also have a ratio of units, meters per second. The question says that I need to find the velocity. Velocity is a rate of the top of the ladder at time t equals 1. So I'm just going to make a note here. When it says find the velocity, there we go. Velocity is a rate. Okay. And if I'm asked to find a rate, I'm asked to find a derivative. I need to find the derivative related to the distance the top of the ladder is from the ground at time t equals 1. All right. This sounds like fun, right? The first thing I'm going to do is I'm going to draw a picture. And while I'm not an artist, pictures certainly help me. And so in my picture, I have this wall. And we would like to assume, right, that a wall forms a 90-degree angle with the ground. And I have this ladder, and I know that it's a 5-meter ladder, excuse me, that is up against the wall. This is fixed. And I know I had talked in the previous problem about fixed numbers. In the problem from yesterday, the farmhouse problem, the fixed rate was one of the legs of this right triangle. It was the distance between the farmhouse and the highway. In this case, my fixed length is the length of the ladder. Okay, so it seems like when we have these right triangle problems, there is a fixed side. The other sides are going to be variable. In other words, as my ladder starts sliding down the wall, this distance here is getting smaller. And as my ladder slides down the wall, the base of that ladder is going to get further from the wall. So this distance here is going to get bigger. I'm going to say that again. If my ladder is sliding down the wall, then the leg here, this distance here is going to get shorter. And as my ladder slides down the wall, the base of that ladder is getting further from the wall. So this bottom distance is going to get longer. Okay, so that's what you have to consider. That's what you have to visualize here as we go to think about this problem. And again, I have this right triangle, and within this right triangle, I'm looking at side lengths of this right triangle, which means I'm looking to use Pythagorean theorem. And again, Pythagorean theorem is that a squared plus b squared equals c squared, okay? And it doesn't matter what you call your side lengths. In this particular case, if you want, you can call this a, you can call this b. I should define these variables. The question in blue says, find the velocity of the top of the ladder. Okay, so A represents distance of top of ladder to the ground. And B then is going to represent distance of base of ladder to the wall, we'll say, right? Because it's already touching the ground. And so it is really important that you identify what these pieces represent, because when you go and find the derivative and you go to substitute in the values that you have to know the correct spot to substitute those values. The other thing that I do want to define, and I know I'm running out of space, per the usual it feels, is t, and t is going to represent time. And especially in this problem, since we are given time, it feels very appropriate to identify that I have this variable t for time. Okay, so again, I have a squared, and again, you could write this as a of t, right? You could say a of t squared plus b of t squared. Well, c is the length of the ladder, and c is fixed. No matter what, that ladder is always 5 meters long. And so before I take derivatives, I can go ahead and put that fixed number in. And I only put the fixed number into my equation prior to a derivative. I don't put in any other numbers prior to taking the derivative, only the fixed number. The only reason why I like this a of t is because, again, we have this t to deal with. It also feels difficult to manage finding this derivative with all these letters. So this would be similar to saying a squared plus b squared equals 25. I just like to keep in mind that both of these a's and b's are functions, just like the y is a function, with respect to time, the independent variable. That means that when I go to take the derivative with respect to time, so d dt of each of these terms, again, my independent variable is time, so I'm taking the derivative with respect to time. The derivative of the a function is 2a times a prime. Okay, because a is not the independent variable, I need to, apply these general derivative rules and multiply by the derivative of that function. A is a function of time, okay? Plus b is a function of time. So the derivative of b is 2b times b prime, times the derivative of that function with respect to time. And 25 is a constant, so the derivative of 25 is 0. Now let's see what information I have to substitute in. A 5-meter ladder, that was fixed, already used that number. Okay, the bottom of the ladder is 1.5 meters from the wall at time t equals 0. Okay, so at time t equals 0, I know the initial that this length here, if you can see, I'm going back up to my drawing. This length here at time t equals 0 is 1.5 meters, okay? I also know that the rate, b prime, that the ladder slides away from the wall is 0.8. And I know that this is going to be a positive rate because the distance is growing, okay? Okay, so again, I know that my distance away from the wall is 1.5. I know the rate at which that distance, that length of B is changing is 0.8, but I want to know information about what's happening when time is 1. Okay, so what that means is, here we go. What that means is this. Currently, I know that when time is equal to 0, that the distance away from the wall for the base of my ladder is 1.5. What would that distance be when time is 1? Well, if the distance is changing by 0.8 meters per 1 second, and that distance is growing, then after 1 second, I go from 1.5 to 2.3, right? I'm adding 0.8 meters every second, okay? So at time t equals 1, the base of that ladder would now be 2.3 meters away from the wall. Okay, so here's what I know. That my b, the distance that the base of the ladder is from the wall at time t equals 1 is 2.3. I know that the rate at which that base, the distance between the base of the ladder and the wall, the rate at which that distance is changing is 0.8. That's the b prime. We had that written here in our picture. And I also know that I am trying to find a prime, right? It says find the velocity, which is a rate of the top of the ladder at time t equals 1, which means I'm supposed to know what a is. Well, I don't know what a is right now per se, but I could use Pythagorean theorem to figure that out, right? A squared plus, remember, I'm focused on what's happening when the b value is 2.3. So when I go to do this Pythagorean theorem, I'm going to do 2.3 squared equals that 5 squared, or the 25, right? And so I need to do a little calculation to do this, right? I'm going to do 25 minus 2.3 squared. I'm going to take the square root of that number. I don't need the negative version of that because we're talking about a distance. When I do that, I get about 4.44. And so that's going to be how many meters off the ground the top of the ladder is. Okay, that's this distance right here at time t equals 1. Okay, and now I'm going to do some math to isolate this a prime, right? I'm going to do the calculation here. I'm going to subtract that. I'm going to divide by this 8.88. And when I do that, I get that a prime is about negative 0.41. And then I need a label. This is a rate. And so when I have a rate, my label should be a ratio, meters per second. And it should be negative because, as I stated earlier, this distance here, this vertical distance is shrinking. It's getting smaller and it's decreasing is another way to say that, which means I should have a negative rate. Okay, so long story short, when it comes to these problems, we should draw a picture if we can. Be aware of what formula to use. We're taking the derivative with respect to time, and we have to pay attention to the information given to us, know how to use that information in order to find the final answer, and that final answer should include units. All right.